Welcome to This Explainer. Today, we're diving into a genuinely massive engineering challenge, powering an isolated offshore oil platform. Imagine a completely self-contained steel island sitting miles out in the ocean, generating its own electricity with zero connection to a mainland grid. It is an absolutely fascinating world of precision math and extreme survival engineering. So think about it. How exactly do you power a city that's just floating in the ocean? Imagine you're an engineer. You're handed a completely blank sheet of paper and told to design this electrical system from scratch. You can't pick out a single cable, a generator, or a transformer until you figure out one fundamental number. How much power does this plant actually need? Guess that load wrong, and you're either building a grid that catastrophically trips on day one, or you're wasting millions of dollars on completely oversized, inefficient gear. Okay, let's tackle this blank slate problem. We have to look at the power demands not just as one giant lump sum of electricity, but as specific components that behave very differently over time, and especially under stress. Here's our roadmap for solving this puzzle. 1. The high-stakes power grid. 2. Categorizing the electrical load. 3. Calculating total plant loads. 4. The N1 philosophy. And 5. Load shedding and survival. All right, Section 1. The high-stakes power grid and the house analogy. To really wrap our heads around how engineers prevent oversizing these grids, think about the plumbing in your own home. When you size water pipes for a house, you absolutely do not assume that every single tap, shower, and toilet is going to be running full blast at the exact same time, right? If you did, your pipes would be huge and incredibly expensive. Well, the exact same logic applies to these offshore platforms. We just don't assume every piece of electrical equipment runs simultaneously. Moving on to Section 2. Categorizing the electrical load based on criticality and duty. You've got to ask yourself a very serious question. If the power suddenly dies, what happens? Does it jeopardize human safety? If the answer is yes, that's a vital load. Think emergency shutdown systems and fire alarms, which need uninterruptible power supplies. Does it stop the actual product from being manufactured? If yes, that's an essential load, like your main process pumps. Or does it just turn off the lights in the kitchen? That is a non-essential load, like the galley or the workshop. Then we have the second dimension, the duty category. This basically defines how often the equipment actually runs. Continuous means exactly that. It's running 24/7. Intermittent means it runs for just a fraction of the time, maybe less than 30 minutes an hour. And standby means it's usually fast asleep, not running at all unless there's an emergency or a very specific need. Section 3. Calculating total plant loads by combining those dimensions. To make absolutely sure we don't end up with an oversized grid, we apply what's known as a diversity factor. It's essentially a rule of thumb multiplier based on how the equipment is used. For continuous loads, we multiply by 1.0 because, well, they're always on. For intermittent loads, we might multiply by 0.5, basically cutting their assumed power demand in half. And for standby loads, we use a factor of 0.0 for our normal day-to-day operation estimates because they just aren't running. So, the real magic number here is the total plant running load, or TPRL. This equation gives us the everyday operational power demand of our island fortress. It's the diversity factor for continuous loads multiplied by the sum of those continuous loads, plus the diversity factor for intermittent loads multiplied by the sum of those intermittent loads. This formula right here, that is the absolute foundation of our master load schedule. By crunching these numbers accurately, engineers ensure the main gas turbine generators are perfectly sized. Because if you build in too much capacity, those turbines run lightly loaded, and that gives you terrible fuel economy. Which brings us to Section 4, the N1 philosophy. Listen, the N1 philosophy is literally the cornerstone of all oil and gas power system design. This isn't just some math formula for efficiency. It is the ultimate dramatic survival mechanism for our offshore fortress. The rule dictates that if any single generator suddenly fails, the remaining units, the N-1 units, must be able to instantly step up and supply the entire plant. Picture this. You've got your N generators humming along perfectly. Suddenly, boom, one generator suffers a catastrophic fault and trips offline. The electrical demand of the platform hasn't dropped a single watt, but your power supply just took a massive hit. Those remaining N-1 units must be capable of immediately absorbing this huge electrical shock without totally collapsing the whole grid. To guarantee survival, engineers use a very specific formula to calculate the load factor, or FI.
They take 100 times PL, which is the total plant consumption, and divide it by PG, the generator rating, times N-1. By isolating these variables, they know exactly what their survival margins are for normal times and post-disturbance disasters.
During normal operation, the system targets a nice, comfortable green zone, usually a 70 to 85% load factor for maximum efficiency. But if one of those generators trips, the system is designed to accept a brief, intense red zone spike. We're talking a post-disturbance overload of up to 125% while it scrambles to shed load.
And that leads us straight into Section 5, load shedding and survival. Here's the catch. Gas turbines have a very, very poor tolerance for overloads. A massive 125% spike can cause a rapid drop in electrical frequency, which could trip every remaining generator and cause a total blackout. So how does the system survive? High-speed load shedding. This is an automated, vital defense mechanism. A highly sophisticated computer system anticipates the failure and acts in literally milliseconds. It computes exactly what must be sacrificed to save the rest of the grid.
The survival sequence plays out exactly like this. First, a generator fails. Second, the remaining units eat that massive 125% overload, but just for a split second. Third, the system instantly and ruthlessly sheds the non-essential loads. It completely cuts power to the workshop, the galley, non-critical ventilation. By sacrificing those low-priority areas, the power demand plummets back down to a safe level. And fourth, the plant stabilizes, allowing the vital and essential systems to keep everything safe and producing.
And that wraps up our explainer on estimating electrical loads and the incredible N1 philosophy. It's just an amazing look at how engineers balance everyday efficiency with these dramatic survival tactics. It kind of makes you wonder, right? If an isolated offshore platform can mathematically predict, absorb, and survive the sudden failure of its own core systems, how might we engineer that exact same N1 resilience into the fragile systems of our own daily lives? Think about that. Thanks for joining me.